Okay, section 2.3, continuity. Hopefully this will be a very brief section. The function y equals f of x is continuous at an interior point, C, of its domain if the limit is the same as the function. So this is saying if I have a function and it's going along and it is approaching some y value, if it actually goes to that y value, it's continuous. If all of a sudden there's a hole or a jump or an asymptote or other things that we're going to talk about in one of the later slides, then it is not continuous. But if it goes where it says that it's going to, then it is continuous, right? So here would be a point of discontinuity because the limit would be this y value that it was approaching and it is not equal to the function is, right? If it was actually filled in, then this would be a continuous function because the limit as x goes to c of the function is always equal to what the function actually is at c. What if a function stops and ends somewhere? Well, then the endpoints are continuous. We have to look at, for the left endpoint, we have to look at the limit as x goes to a from the right. And for our right endpoint, we have to look as x goes to a from the left. Okay? So for this point here, this would be continuous at that point because the function is going exactly where the limit is, right, where we thought that the function was going to go. If all of a sudden this, instead of this endpoint, there was just a hole there, then it would not be continuous. And here, same thing, the function is going exactly where we thought it was going to, so the limit from the left is the same as what the function actually is, so it is continuous at that right endpoint. So on our entire interval, it's continuous to the left, it's continuous to the right, it's continuous everywhere in the interior, right, in the inside of the interval. Therefore, it is continuous everywhere in the interval. Call this A to B. It's continuous everywhere on the closed interval A to B, including A and B. Next, we have if a function is not continuous, then it is discontinuous. A function is continuous on an interval if it is continuous on every point in that interval, as I already told you on the previous page. And a whole function is continuous if it is continuous at every point of its domain. And this is the important part. Okay? If it's not part of its domain, then we don't check to see whether or not it is continuous at that point. So say, for example, I have 1 over x. 1 over x looks like this. It only exists when x is less than 0 and when x is greater than 0, not when x equals 0. So my domain is negative infinity to 0, soft parentheses, union, soft parentheses, 0 to infinity. So this is where the function exists, and everywhere on those points, the function's continuous, right? Here at x equals 0, no, it wasn't continuous, but that is not part of the domain, so we're not looking there to see whether or not it's continuous, right? It doesn't exist there, so we wouldn't check it, okay? If, for some reason, I had a piecewise function, and it was defined to be 1 over x, except for at 0, it's defined as 0. Well, now all of a sudden, my domain is all real numbers, and it is not continuous everywhere, because it's not continuous at x equals 0. So this is with my green dot right here. My domain is all real numbers, and this is not continuous. Not continuous, because at 0, I checked it, and the limit as x goes to 0 from the left is negative infinity. The limit as x goes to 0 from the right is positive infinity. Neither of those are equal to 0, so therefore it's not continuous. Whereas my original function was continuous if I only looked at the black. Because the only place that it was discontinuous was at 0, but we didn't care about it because it didn't exist. Okay, types of discontinuity. If we're looking at the entire function, right, then first of all we have a removable discontinuity. So if I have a graph that was going along, and all of a sudden it decided to have a hole, and then it kept on going. That's called a removable discontinuity, because if I remove it from the domain, like I did right here, I removed x equals 0 from my domain, then it makes like a continuous function, right? So right here, with whatever x value this is, if I take that away from the domain, then it is now continuous. So it's called a removable discontinuity. Let me just have a second example. You could have the hole and then it's filled in someplace else. So say it's right there, okay? So either there's just a hole, or there's a hole and then it's filled in someplace else. removable discontinuity. Jump discontinuity says we're going along and all of a sudden we go somewhere else. Okay, so it actually jumped. Over here, we have to show the difference between these two because removable, we could say, all right, well, if I had filled in that dot, then it would have been perfect. Well, here, we can't just fill in the point that we're missing and then it'll be continuous because then my y value still wouldn't match up. So my limits are not equal from the left and from the right. And infinite discontinuity is when we have vertical asymptotes, not horizontal asymptotes. So if it's going to positive or negative infinity, then that's a point where it's discontinuous. And the last one is oscillating. Some functions will be oscillating back and forth instead of approaching a particular value. And so the common example for this one is sine of 1 over x, which as you go towards 0, gets, oh, this is difficult to draw, right? Gets closer and closer together. Okay? So that's a really bad drawing of it. You can look it up on your calculator if you're interested. So this is sine of 1 over x. There's also a picture of this one in your book. Sine of 1 over x, and make sure when you're graphing it, you're in radians. Okay. There is no actual limit as x goes to 0, okay? Because it's just oscillating between -1 and +1 faster and faster as I move towards the y-axis. So this is oscillating, and therefore it is also a point of discontinuity. Next. All right, on to our examples and then the homework, and that's it. Identify the points and types of discontinuity. Give a formula for the extended function that is continuous on all real numbers. Okay, so first of all, what I want to do is I want to factor the numerator and denominator, because I can already see that at x equals +1, I'm going to have 0 in the denominator and in the numerator, so I get 0 over 0. So hopefully those will cancel out. This is a good opportunity to remember how to factor the sum or difference of cubes. And remember, if I have a cubed, I'll write it up in case you don't remember, minus b cubed, then factored, it equals, first we do a, b, a squared, ab, remember this is on our PowerPoint, and b squared, the pre-calculus PowerPoint. And then you go back and do the signs. Same sign, opposite sign, always positive, right? Relating to this original sign. Same sign, opposite sign, always positive. So always remember your SOAP with cubic functions. Okay. Okay. So factoring this one, right? What is being cubed here? Just x, so x is my a. What's being cubed here? Just 1, so 1 is my b. So I get x squared, 1 times x, which is just x, b squared, which is 1 squared, which is 1. Divided by, and then we just plug in the sign, same, opposite always positive. This is the difference of squares, x plus 1, x minus 1. And I can see that they will cancel very nicely. Let's do it in a rainbow color. Oh, that was a horrible idea. And you can't see behind it. Okay, stick with the green. Cancel, cancel. Okay, and now the function, oops, the function is fine at x equals +1. Okay, so what are we doing? So identify the types of discontinuity. We would have x equals -1. We're going to have a vertical asymptote at x equals -1. Vertical asymptote, so that's our infinite discontinuity. Infinite discontinuity at x equals -1. And then this cancels right here. Okay. So therefore that gave us a hole. So what happened at that hole, that could have been removable or jump discontinuity. So if I take a look at, well, actually, if it's just a hole, then really it's going to be removable discontinuity, so I don't even need to graph it. So removable discontinuity at x equals 1. So, give an extended function that is continuous on all real numbers. Well, I can't give an extended function that's continuous on everywhere, right, because of this infinite discontinuity. I can't just get rid of a vertical asymptote. So what I can get rid of, though, is a removable discontinuity, and then it'll be continuous everywhere except for at x equals 1. So the extended function is saying if I cancel these out, right, I'm just ignoring the removable discontinuity, the fact that I have a hole at x equals 1, and my function is going to look like this, right? We know from pre-calculus that in order to graph this function, we can graph, once these are canceled, we can graph this, and that's what the function will look like, and we just put a hole at x equals 1. So our extended function is f of x equals x squared, plus x plus 1 over x plus 1. Makes it continuous, I can't write very well today. Continuous at x equals negative 1, or positive 1, sorry, because we got rid of this. So at x equals positive 1, right, we cannot come up with an extended function to get rid of the infinite discontinuity at x equals negative 1. Cannot get rid of this one right here. So we cannot make it continuous everywhere, but we can at least make it continuous at x equals positive 1. Okay, so that's what we can do. Okay, so this function is continuous everywhere except for at x equals negative 1, because we get 0 in the denominator. Next. Okay, this one, also, we can see that we're going to have to, well, not factor in this case, we're actually going to make a second factor. Okay, we have a problem when we plug in x equals 4, because then we have square root of 4, which is 2, minus 2 is 0, and then we have 4 minus 4 up here, which is also 0, so we have 0 over 0, so we need to do something differently. And the way that we do this is we rationalize the denominator. So we multiply the numerator and denominator by square root of x plus 2 over itself, and I'm always allowed to multiply a function by something over itself, because that's just multiplying by 1. And what's going to happen on the denominator? I will get square root of x times square root of x is x. It's a difference of squares, so my outer and my inner terms cancel. Then I have minus 4. Well, that is going to cancel with this first term in the numerator, so don't distribute the numerator. Okay. X minus 4 times square root of x plus 2. Cancel, cancel. And I automatically have my extended function. So my extended function is y equals square root of x plus 2. Okay, the only other thing we need to do is talk about the points of discontinuity. So it is discontinuous at x equals 4. And what type of discontinuity? Well, because those cancel, then, right, yeah, then it would be a removable discontinuity. Removable discontinuity at x equals 4. And it must be removable because we just removed it. Like I said before, if you had a jump discontinuity, you couldn't just call it a new function. You couldn't just come up with this new extended function that ignored that jump, right? Because here we're just going back here, right? So say this was some sort of quadratic divided by a linear function, right? And if I could cancel two of those terms, then that line that I'm left with is that line filled in, filling in that one point right here. Okay? And I can't do that for a jump discontinuity because this is not just one big function where I can just ignore this part where it jumps right here. Last question is sine of x over x. Well, what happens right here? Well, let's see. Okay, so this is bad at x equals 0. And you guys knew what sine of x over x looks like. And it looks like this, where it oscillates more and more as you go to the left and to the right. Really difficult to graph sine, or anything trig related. And we obviously cannot plug in x equals 0 because we would be dividing by 0. So we have a hole right here. So again, it is removable. And we can fix it. Removable. Discontinuity at x equals 0. Okay, so in order to remove it, well, what function do we know that looks exactly like this, only a filled-in circle right here? Well, we don't know anything that does that. So we need to actually make a piecewise function. So the function would look like sine of x over x everywhere. And then at x equals 0, it's going to, well, where would that be filled in? 1, right? You know what that looks like because we know the limit as x goes to 0 is 1. So this is when x equals 0. This is everywhere else, so when x is not equal to 0. Right? Negative infinity up to 0, soft brackets 0 to infinity, everywhere except for at 0. So there is our extended function. Okay? If we had a function that looked just like this and had that point filled in, we would use it, but we don't. So we just made one. We just filled that right in. Okay? And all you have left is your homework. Hopefully this was easy and a little bit quicker than some of the other ones. I will see you tomorrow.